First off, pretty nice crowd. Thank y'all for coming. Name's Dave. Long-time computer geek. Started on the Color Computer 2. Moved up to the Commodore 64 and have bounced around to just about anything and everything ever since, including XT, AT, all up the chain. And part of that technology phase is why we're here today. Today we'll be going over some of the fun I've had trying to recover data from a hard drive that some of you may already be aware of from about a year ago. We'll get there in a sec. Okay. So again, journey to recover data from an old drive for clone PC. So how many of y'all have seen this video? How many of y'all know this one? A couple of y'all, okay. For those who don't know, this video came out about a year ago after last VCF by a good gentleman named Dave Lovett, whom y'all may know as Usagi Electric, over in the exhibitor hall. He put this video out after he received this PC clone from the EDS Corporation. Found it, I believe it might have been during the computer reset days. I'll have to double check on that. So, long story short, that drive in the center right there was an RLL formatted drive that during this video he and AJ from Forgotten Machines had tried to recover the data from. In the end, however, they were unable to read it, but they did back up the information at its lowest level, the magnetic flux transition. We'll get there. So this is where I started going down, pun intended, the rabbit hole. So when I started this whole journey, all I really knew and remembered from MFM and RLL hard drives from back in the day was take the drive, plug it into 3 cables: power, a 20-pin data cable, and a 34-pin control cable. Plug those cables into your drive controller, power everything on, and assuming that those devices were already matched, hope it worked. Back in the day, unlike modern hard drives, when the controller was formatted, it would have to be paired with its controller because the controller specified how the data was laid out. You can't just take that drive, plug it into another controller and hope it worked without completely reformatting it, laying down a new low-level structure. Then you could put your data on it. So at the lowest level, basically there's a series of heads that have little magnets and magnetic sensors on them. And when you want to write data, it takes that magnet, moves the alignments of magnetic media, switches the alignment around, and it's in the positioning of that alignment where your data eventually comes from. Goes through a few stages first, and basically converts that data across. Well, we'll see how it gets there. How many of you remember that little command down at the bottom? Okay. That was generally, at least for Western Digital controllers back in the day, the way you would initiate a low-level format. You would use the DOS debug utility, enter that command, and in the ROM for the controller, it would start laying down a new low-level format after asking you a few questions about the drive. You know, how many cylinders, how many heads, etc. So again, it's kind of a visual perception on how that magnetic data is stored. Different types of head setups. You know, a little dry, but I know for me personally, I'm a visual learner, so charts and graphs, pictures, awesome. Okay. So now we're going to move on to the actual encoding and how the data gets set up with the magnetic pulses. So basically, we're focusing on RLL encoding today. It generally gets lumped in with MFM encoding because it uses the same technology, just with different parameters. It still is based off the magnetic transition information. You'll see it written as RLL 2,7 in some cases, if they really want to get a little technical on it. Basically, the numbers dictate how often the transitions can occur between different polarities. The first number, the 2, basically says that, let's say you have a north polarity on your magnet. You flip it to a south. That's considered a transition. That number 2 says that you're allowed to have 2 more periods before you have to have, no, actually, hold on, let me back that up, my apologies. That means you can have a minimum of 2 non-transition periods before you have to transition, but you can have a maximum of 7 transitional periods, or non-transitions. It's a little confusing, I know. I've got a graphic coming up to kind of lay that apart. So again, pictures to help out. So you can see at the very front over here, let's see if I can make it, okay. You can see over here how you have, at the beginning we're starting just with no transition. Then you can see it goes up, so you have a transition, 2 more non-transitions, and then the transition down, and so on and so forth. But if you go off the 2,7 encoding, you'll notice I threw a curveball in here. That extended run over there is 10 non-transitions, and you can't have that. It's an invalid encoding. So that can be a way you can actually tell if the data on the drive may have been corrupted over time. If you have a lot of those invalid periods, then the data might be experiencing a phenomenon called bit rot, to where if the data is not updated periodically, it can lose its stability as one magnetic field tries to affect the others over time. And I know earlier I mentioned AJ of Forgotten Machines. I noticed you. I wasn't going to leave you out of this, so he came in. So welcome.
Thank you.
So the way this works to get our actual data back is these transition patterns can be basically fed through a lookup table that's on the controller chip for each controller. And different manufacturers, even different controller families, can have slightly different lookup patterns. So it takes the transition information, bounces it against this lookup table to convert into your actual data bits that you get through. For RLL 2,7, it'll take blocks of 4, transitions 6, or 8, and convert those into half of their binary equivalents. So it'll go to 2, 3, or 4 binary bits. The cool thing about MFM encoding on the other side is it's generally standardized across controllers. One MFM encoding, basically the MFM encoding is going to be the same whether you go from Western Digital, Seagate, etc. RLL, as mentioned, different companies, different families can have slightly different encodings. So that's part of the reason you can't just take a drive from one manufacturer, plug it on another manufacturer's controller, and be able to read the data. You can see here that the 2 entries in the center are basically flipped between Seagate and Western Digital. Okay. So we've got an example in here, and this is where we start getting into the nerdy math of it. We're going to take the hex value of 42, and we'll break that down and we'll get the flux transition information that it will encode to down at the magnetic level. So we take it, we get its binary equivalent, okay? And then what we do is we start at the beginning with the 0, 1, 0 and 0, and we see from our data column exactly how many of these bits we can take at one time that match up with that data column. In this instance, we can break it down to the 0, 1, 0, which matches, the 3 zeros, which will match, and then the 1, 0, which will match. We go through the lookups, we convert the 0, 1, 0, and it comes out to this pattern, which, again, at the magnetic level, represents that there are 3 steady states where there's not a magnetic transition. The 1 shows, okay, now we're going to have a transition, and then the other 2 show that we're going to stay at that new level. So then we go with the 2 zeros in the center, goes to a transition, none, none, another transition, none, and none. And finally, the last 2 bits, which will go to no transition, a transition, and 2 nons. So in the end, when you look at the transition information from the disk, this is the pattern you would expect to see that would encode the hex value 0x42. However, like every good story, there's more to it. That is good at representing this section, but depending on what data comes before it and what data comes after it, can influence what that entire bit stream could look like. Because we could have another, let's say we had the next byte of data started with the 2 high bit set. We would now have a 1, 0, 0, 0 after this, but it could only have a high bit set, a 1, 0. So we could have the next 0, 1, 0, 0. That would be valid as well. It basically comes down to one giant stream that has to be broken down chunk by chunk and converted. And by all means, if anybody has questions, whatever, I can intersperse them. If y'all need me to slow down, if y'all want me to speed up, just let me know. Yes, AJ?
So the RLL encoding, the maximum number of non-transitions in any one period is 4, 3?
It should be 7.
7?
7.
That is huge.
Yeah, that's why the timings on it, a lot of systems that I've seen have had self-adjusted PLL clocks. So it can actually take a look at the transition stage and adjust a clock to sample the data as it goes.
Oh, that's what the 2-7 means.
Correct.
I missed that part. Thank you.
No worries, no worries. So yeah, basically you can have a minimum of basically transition, none, none, transition. You have to have at least 2 in between. And then you can have up to 7, and then you have to have another transition. Without that, if you try to go over 7, it can actually throw off the sampling timing and can cause the rest of the bits to drift. So that's why they limit it to 7. Yes, sir?
So how it encodes a certain binary stream is, does it look at the entire sector at once and determine how that's going to be encoded? So that's ultimately like the smallest chunk of data you're going to write to the disk?
So, full disclosure, I haven't looked at specific controller chips in regards to the maximum data reads and writes. I know that generally for the device that I'm going to discuss, which looks like it's actually here right now, Preview, the David Guesswine MFM emulator, is a central part of this as well. That's a device invented that can both read and in some cases write to MFM encoded drives. Asterisks, we'll get there later. So that device specifically goes an entire track at a time. It reads the entire track in because you have to look at its index mark to see where the start of the sector data is. But then based on drive interleave and a couple of other settings, the first sector may not be the first sector. So it starts reading that data in and decodes it, and we'll get to that a little later on too. So, okay, cool. Oh, What do you know? Good timing. So I was just talking about this. So a gentleman named David Gueswan, many years ago, invented this device that can basically read data from an MFM hard drive at the flux transition level and is actually pre-programmed to decode that data based off of information gathered from different MFM controllers. It has a lot of different, like IBM, Seagate, Western Digital, a lot of different models already programmed into its software so that you can plug the MFM hard drive directly into that device, plug it into Ethernet, shell into it, and actually pull not only the raw magnetic transition information, but if that drive is laid out with a controller that it knows about, it can do the data decoding and provide you basically with a disk image that you could either DD, raw write, or even load into a VM or an emulator. So this device is kind of the cornerstone for some of my research as well. But big caveat, the code currently only supports MFM hard drives. It is not compatible with decoding RLL data publicly. So that issue, that's actually been an outstanding issue. It's issue number 8, ask me how I know, on the GitHub for the project.
How long ago was that? Like, submitted?
So the issue on the issue tracker has been there 10 years as of this October. I started looking at the code a little under a year ago after the video came out that Usagi put up. Because I noticed during that video, again, it didn't support RLL modes, and there were a couple things that he had tried to access the drive that weren't working. Trying to boot into DOS, get access to it, it wasn't recognizing the drive, it wasn't reading the partition table, so it couldn't set it up. So I spoke with Usagi, and I was basically, hey, let me try a couple of other things to see if I can get to it. I had an old copy of Slackware Linux. I still have an AMD K6 too. Used to be my daily driver in '99. Still works all these years later. So I'm like, you know what? Let me see. If you're willing, let me see if I can get to the data. Got the drive, started playing with it, booted up Slackware. Nothing. So I started thinking about it. I was like, all right, let me see if I can do anything with this transition file that was dumped during that video and see what I can get from there. So I grabbed David Gueswan's code for his device, started looking at the code from MFM util, which can actually do the translating from the transitions to a hard drive image file. And it just wasn't clicking. I didn't know the first place to look in that code. I tried to figure out where it did a lot of the analyzing, and it wasn't working, wasn't clicking. I looked at it off and on, but that hamster just didn't want to spin on his wheel for some reason. So what I ended up doing at one point is taking a break from that code. And I started working on some code to see if I could understand the transition file format a little better myself. So I put that on hold, and I started working on a separate C program to try to read that data in directly and parse it myself to see if I could get it translated. And I was able to make some progress on that. I was able to start seeing translated bytes here and there, but I quickly noticed that something still wasn't quite right. So then, fast forward to late March this year, the hamster got his caffeine. Something finally made sense. So I was looking at the raw transition data, and I was noticing a few places where there were some invalid runs. And I started playing with those a little bit. and trying to kind of work the clocking code a little bit differently. And I also looked around and found some more samples to look at. And this is what really drove the point home for me. I went to bitsavers.org. For those who may not be familiar with it, beautiful resource for a lot of retro information. Has a pretty good archive. Check it out. So I grabbed a few of those RLL encoded samples and started looking at those, not only looking at the raw transitions, but throwing those through my code. And those were starting to convert a little better. So I'm like, okay, I might actually be onto something. This might be working. So I kept working with those files. And I finally broke down and I contacted the author himself. I sent an email over to Mr. David Geswine, and we kind of went back and forth, and he finally got me on the right path for a couple of things that I was off kilter on. And the cool thing about the timing on those conversations is right around the same time, another developer had made a contribution to the code repo with regards to parsing RLL data for his Western Digital drive. So I apologize if I butcher this gentleman's name. Mr. Polhinning-Kamp provided a Python script that would parse through transitions. It didn't know the exact file format from the Geswine device, but you could basically pull out a block of transitions and it would actually convert those transitions into user data and a little bit of other hard drive low-level data. So that is what pointed me in the right direction, that said after each block of data, you have to reset your state and listen for a specific mark before you can start trying to decode again. That's what was throwing me off. So basically, his code also showed me that there was certain handling with regards to a CRC and ERC error checking code in each block of data as well. So from there, I started looking back at Mr. Geswine's code, and things were starting to make more sense. So what I basically did is I started with the MFM specific code. I did the parsing code that did the recognition for these address and header marks, and basically copy, paste, edit, fix, and implement any additional functionality for RLL specific things, so that now you could break out and do MFM and RLL separately, but it would still try to analyze your device to figure out which controller it came from first. So I took some of the code. I know sometimes software development houses don't like the word refactor, but so I did. Took a lot of the common functionality that would be present for both, factored those into some common headers and source files, and then basically it splits out each controller family has an MFM and an RLL equivalent based on the products available. So here's kind of a sample of some of the source code edits, implementations. You can see the Western Digital table I had over there. I have another table for C8 as well. Some of the processing. Fair disclosure, this code is already out of date because there have been some newer edits since then. But basically, I sat in, I got to work on it. And the big thing about these low-level formats is it's not just user data. There is some metadata there that each controller uses to keep track of certain aspects. For this case, we have two major blocks. We have an address block and a data block. The address block basically breaks down where on the disk that data is located with regards to the cylinder. In this case, this is cylinder 50 once you convert it. This byte breaks down into the head along with a couple of other defining marks. For instance, whether it's a bad sector, if it's been marked, or if it's a replacement sector that you can use later for a bad sector. Then we have the sector number itself. In this case, this was sector 22, I want to say 16, 6, yeah, 22. And then these 2 bytes are a 16-bit CRC. The cool thing about that address header is if you feed that entire block into the CRC function and everything's correct, your result will always be 0. Quick way to know if that's gotten corrupted. So what will happen is the way it's set up with the transitions with the data at the low level, what you'll have is a block of pad data, usually 33 hex for the RLL controllers in the Western Digital family. You'll have just a run of 33s, 33s, 33s. Then there will be a very specific bit pattern that you look for that notes basically that A1 equivalent. It's supposed to be A1, but it's intentionally encoded incorrectly as kind of a way to identify, okay, this is where I need to start listening. So we use an equivalent of A1 for that mark. The FE notes that it's an address header, but a couple of the lower order bits are also used to encode the high number of the cylinder as well. So if you have more than 256 cylinders, that's how you account for the higher numbers. So that could be anywhere from FF down to F9, depending on where you are on the disk. The data marks, the same type of thing. What you're going to do is you're going to have those 33s in between the address mark and the data mark. And then again, now you're listening for that bit pattern again for the bad A1. You pick that out, you know, okay, we should have data, game time. It starts pulling the data. The next one's going to be an F8. And then you're going to have X number of data bytes that come across until you hit the value for the maximum number of bytes per sector, which is also encoded in that status bit in the address header. And then in this case, the last 7 bytes of that block are an ECC code of 56 bits that, again, it can use to not only validate the data, but to a certain extent can be used to recover bad data as well. Don't ask me on the internals of that one. I haven't dug into those weeds yet. So basically,
I'm seeing this as, so you're seeing this as a stream,
correct,
but you're just looking for these patterns. These patterns are your address mark and your data marks
correct,
coming out, okay.
correct.
So you may have address mark, right, all just jumbled up in there, or?
Well, that's where you start getting into a value called sector interleave, which is something else they threw at us back in the day.
Thankfully, that's not unique to RLL.
Yeah. So sector interleave was kind of a way that they would toy with increasing performance. So on the disk, there is a separate area where they have a mark called an index mark. If you're familiar, anyone who's played with floppies, the 5 1/4 inch floppies, that little hole off to the side, or in some cases 10 of them for certain disks. That little index mark, you'll notice as the disk goes around, it'll do a hole once per rotation. The hard drive has the same concept. As soon as it hits that index mark, it knows it should start reading the first sector of data from that track and go around. Well, depending on how that interleave is set up, that first sector could be sector 1, but the next sector is not going to be guaranteed to be sector 2. Depends on the interleave value. It could be sector 7, and then sector 13. And then as it goes around, it fills in the values in between as it wraps around. For RLL, you'll generally have a max sector count of 26. Not always set in stone, but that's the generally used value. So that's where the data translation gets a little hairier, is if you're using an interleave value, because when you go to analyze it, now you have to kind of skip around if you want to reconstruct that in order. So, yes, sir.
Yeah, you mentioned the address mark, the A1 is written incorrectly.
That is correct. Basically, because as we went over in the beginning, the encoding, you can have 2 up to 7 non-transitions in between. I don't remember off the top of my head the exact transition pattern. It's like somewhere between 18 and 20 bits, somewhere around in there. But it would normally have been encoded correctly for the value A1, but they intentionally had a bad encoding value in there that you normally won't be able to write because it's not on that translation table. So,
And that applies for all occurrences of the address mark.
correct. And for the data mark as well, for that first value only. And that's how it knows where to sync up for those particular spots. So after I added that code to the guest-line device and started running Usagi's drive through it, you can see some of the debug output. I know a lot of it's cryptic, a lot of it is crazy. The main things I want to point out here, these 3 bytes right here, this would be the sector number normally, and then the CRC. You'll notice that it says it's sector number 0. Again, it verifies down here, sector 0. And for some reason, still looking into it, it's saying it's sector -1, getting it off by 1 in that. Think I know, now that I'm talking through it, where in the code that's having an issue. And for some reason, later on, it thinks it's sector number 69. Still working the kinks out. But, yeah. But, yeah, I walked right into that one. Okay. But as we go on, this is the fun stuff. This is the money right here. This is what we wanted to see. Now, keep an earmark on that last dump back here. Keep an earmark that that's cylinder 50, head number 3. There's a reason for that. This is one of the sectors on that track that was able to be properly decoded. I have a section highlighted in green. Anyone who's good with ASCII characters, that's going to make some sense. If it doesn't, I'll go ahead and break it down to make the sense. So all of those are ASCII equivalents of that quoted string at the bottom. It's a list of numbers. Don't know what they mean. No context for it, but it's data that was recovered from that drive. And that's the big thing. So we go forward. Now, why did I use cylinder 50 head 3? Sounds a little just random. So I sent the dumped transition file to Mr. Guestwine himself. And he took a look at it and started looking through the data and basically said, okay, looks like you have a misalignment in your heads. Over time, in some cases, the older drives, as they're sitting, the heads can kind of move out of alignment. The drives get moved around. They've been powered off for who knows how long. The heads can kind of drift to where it's not right on the data. So he had run into another case like this before. That's how he recognized it. Pointed me to his Google discussion group for the project. And in that article, basically, he had directed another user to a page that mentioned how to modify the device to control the stepper motor on the heads directly so that you can actually step the head in between tracks to do data recovery. A lot of the Seagate models, if anyone has one, can look at the jumper settings in the back, and there's one of them that has a recovery mode in there. Also, pin 16 of the control cable has a recovery mode. If you drop that line low, it'll send the drive itself into a micro-stepping mode, even without the external hardware. So I looked at his write-up on his webpage for doing the other thing, Now keep in mind, at this point in time, I do not have my own personal guest wine device, nor did I have the funds allocated to acquire said device. So I was kind of playing around and trying to figure out, okay, what can I do? So I went ahead. He said that cylinder 50 had 3. The data actually looked good, somewhat. So he said I should be able to pull back data. So that's why I fed that combination in there. I was able to pull back data. There were a few other sectors that came up as well. One of them showed a bunch of file names that made 0 sense to me. But at the end of the day, it's the good news that data was there and that some of it could be read. So the next steps going forward were to design kind of my own, I don't want to say poor man's version, but kind of a smaller scaled back device using parts mostly on hand. Because I've had a couple Spartan 6 FPGAs, I had a couple microcontrollers. I'm like, this should be doable just for the sake of reading the data off. I didn't need to worry about writing it back, doing anything too crazy. So looking through the message forums for the guest wine device, I found a user by the name of Tronics286 who had designed their own reader device. Basic schematic, they had prototype boarded it, but I took a look at that device and I was like, okay, I can use this. I took the design, I made a couple small changes to be able to access that recovery line and also the drive select line. It was jumpered originally. In this case, I made it programmable and ended up with this little board right here. Pay no attention to the yellow wires. That was a result of not reviewing the schematics multiple times and doing them at midnight.
We all have botches.
So basically, this device is similar in functionality with Mr. Guest Wine's original device. Its sole purpose, though, is just to read the transitions off and allow you to dump them to a file. That's all the hardware does.
It won't be doing any emulation.
No, sir. Not at all. But boards plus the components I did not have on hand, which basically the Pico was the only thing I had. Boards plus one set of parts set me back about 50 bucks. It's a bit, but I know that device, for all of its extended functionality, it is a bit more costly. Not that I'm disparaging it. It's a beautiful device, great device. If it fits the use case, go for it. For me,
Well worth it.
I just needed something smaller for now. So the next goal is to be able to get a clean dump, or at least a cleaner dump, of the source drive, get those transitions dumped, be able to convert those back to its original data. And then if I can get enough data back, well, this plan has changed now. After speaking with Dave this morning, the plan's changed a little bit. All he wants back is the image. I'll give him the image back. And he said, Merry Christmas, have the drive. So I'm going to use that drive, and the plan is to see if I can find other models of RLL controller, kind of put an open call out. If anybody is willing to allow me the use of their controller, I can reformat the drive and try to implement those controllers in the project as well. So that's one path I have going forward right now. Ultimately, I do need to get my own official Guest Wine device so that I can get my code reloaded onto it and test it and make sure it works effectively. Right now, I was able to recompile the utilities under Ubuntu, so I can test it on a PC to do the conversion and do the data dumping with my device. Ultimately, it needs to work on the real thing. Additionally, again, code updates, implement additional controllers as time goes on, as equipment allows, so that we can expand that out for the community at large. Any questions?
How many estimate controllers are you looking at?
Um,
Does anybody know any RLLs with different sector out there?
You
honestly,
mentioned Western Digital.
correct.
You also mentioned another manufacturer, right?
Correct. I know Seagate had a line of controllers. Intel had their own line of controllers.
3.
As far as those are the big three that I know of.
And this one you want me to work with?
Yes,
That's
sir.
Western Digital, right?
Correct.
That's what it says.
That is actually, so that card that he has, that he's been looking at right there, that is the Western Digital 1004-27X. That is the same controller that Dave Levitt, Usagi has, that he had originally he was working with. And that one is actually mine. That I purchased in support of this. AJ has been gracious enough to basically say, I will help you. So I shipped him the controller, and he's actually going to go through and format a couple drives, pull some transitions along with the actual image files so that I can basically perform unit testing and make sure the conversion comes out the way it's supposed to. So again, a huge thank you to AJ for that.
You thank me after I actually do it.
You are willing to, and that counts. So, again, if there are any, yes, sir?
I'm struggling with the visualization of the transitions and the maximum, like you said was 7, maximum 7 long transition states.
All right.
How do you determine like the pocket?
So, again, a lot of the older devices, maybe not all, would have a phase-locked loop. And what they would do is they would basically see whenever there was a pulse transition, and they would set that loop based off of an average of timings. So they would do a little bit of polling on that signal for the data. They would start taking kind of an average to set the clocking interval for that PLL, and then from there going forward, it would use that interval to sample.
Yeah,
in between.
if I can here, the sectors on most of these discs, what's between the sectors on the track is something that is often called a preamble and a postamble. And that's simply a transition of pulse after pulse after pulse after pulse. No breaks in the pulse, no zeros, all ones, right?
Mm-hmm.
For let's say 5,000. So let's say we got 5,000 ones. Well, the phase lock, maybe that's too many for this, right?
What?
But a large number by comparison. And so whatever the logic circuitry does, it says, oh, here's a lot of continual ones. I'm going to sync my internal clock to this, my phase lock loop. And then when I see that a sector is beginning, because I see the sector beginning code, the header, whatever that is, the sector header, then I'm going to know, all right, timing is locked in at whatever the preamble timing was. Now we're going to continue on and assume that the timing of that entire sector matches the timing that was set by the preamble before it. I wish I had if I were at my exhibit table, I could actually bring up a diagram of this and show it to you visually.
That helps.
So, caveat.
So come on by if you want to see that.
I
Forgot the shades.
just about to say that. So, no. Cool. Yeah, I definitely check him out. Check out Usagi's table as well. Go get a
We're
chance.
together.
Kind of like setting the like beat per minute of Morse code kind of thing. And that's what the only thing I can think of.
It's similar. It's similar.
Yeah.
Right. So, anybody else? Questions? Yes, sir.
Maybe I missed this, but were you ever able to like determine what the data was that was on the hard drive or on the magnetic disk?
So I have been able to decode a few of the sectors so far from one of the tracks. The next thing I need to do is implement that recovery mode that the hard drive has, because many Seagate models of drive, which this is a Seagate 238R, if you enable a certain signal on one of the control lines, it will tell the hard drive head, instead of a step command telling it to go to the next track that it knows of, it will actually tell it to micro step in between the tracks, where it thinks the tracks are. So you can divide that step from one track down into sometimes 4, sometimes 8 individual micro divisions to try to get a better alignment on the data. And that's what I need to put in right now to see if I can get that to get the data more accurately. The transition file that we've dumped, or that AJ dumped, many of the tracks have data that's kind of, I won't say scrambled, but it's kind of mixed between 2 tracks.
Yeah.
So I tried to average that data between the 2, and it basically corrupted that output for a particular track. So
First said you want micro step, you were just doing the sector steps.
I think the answer is yes. Yeah, and you're actually asking about the image that I took on you saw
Correct.
last year.
Correct.
Yeah. So we just let this device step the drive normally. Track 0, track 1, track 2, and so if the heads are off on if one of the heads were off, then it's not going to line up with the track. And I guess it was enough that we were getting data from multiple tracks, and you can tell that because every sector has its own address built into it, right? The header of every sector knows where it's supposed to be. So if you're on track 0, the first sector should be should say I am sector 1 in track 0. Well, the next sector you get says I am sector 1 in track 1, but the head's on track 0. You know you've got an alignment problem.
And even worse is if it's trying to pull data back, but it is so far out of alignment that it's pulling data seemingly from 2 different tracks at once.
Yeah, it's just all messed up.
Then it merges
It's like
those.
noise on your radio. You can't hear anything.
Correct.
Do you see the same problem with the MF drives? Doing the micro stepping?
Correct. That was actually, it was an MFM drive that Mr. Eswine diagnosed at first with another user on his forums. I can actually show you real quick, if I've got this up. So there's a file I have. Come on. Is this, it should be this one. Oh. Bear with me, I don't Mac very often. Let's see. Choose location. So there's a feature of the Guesswine device where in the software you can actually see kind of an averaging or a histogram of the data it pulled back for a track. On a normal MFM drive, you will see basically a breakdown. It'll show timing data between one pulse to the next, and you'll see a clear peak in that data at 40, 60, and 80 intervals. For an RLL drive, because the timing is a little tighter, because it compresses more data into the same amount of physical space, you'll see peaks at 13, 26, 40, that match up with the different 2, 3, and 4 pulse periods. In this particular case, that histogram, instead of having the defined humps at different spots, it was just kind of spread out, and there were more values in between. I'm trying to see if I can bring that up real quick. I've got a sample that shows that. I just need to figure out how to Mac. Open with other. Okay, how do I? Oh, wait. All right, quick. Renaming a file on a Mac. Ready to go. Which one? No. Negative. Long press, single. Oh, enter. It's been a while. Maybe enter. Enter, do it. Either way, I can just see if I can do this. Where's the bar down here? Do we have, you know what? We got LibreOffice. We can do it with Libre. Cool thing about technology is there are multiple ways to do something. Let's bring you over here. Don't want to spoil anybody else's presentations. File. So we'll come over here. See if I can open. That's fine. Open this. Okay, come on, come on. All right, here we go. So over here.
Yeah.
Come on, come on. There we go. There we go. It's very tiny and very hard to see, but this is actually a histogram that I pulled back off of that track, cylinder 50 head 3, the one I was able to get data off of. Oh, say again? Oh, okay. Come on. Oh, yep, there we go. So, there we go. So you can see, and you know what, let me get rid of these and get a little more real estate here. So you can kind of see as it goes down that there are very well-defined peaks around certain values. These are a little bit different. Unfortunately, the Pico-based device, the timings are a little bit different from the actual guest line device, so it's off by 1 to 2 intervals for each peak, but it's still enough for the code to be able to decode it because it's close enough.
Did you bring any drives with you?
I did not. I was gonna bring Usagi's drive. Yeah, but I was thinking about it and I was like, ugh.
We have some plans. We have some plans.
Okay.
That shouldn't take away from anybody else's willingness to offer help as well, because this is a pretty cool project.
Awesome. Thank you. We'll talk. We'll continue talking. So.
I'm just curious about what kind of clock rates are we talking about with our drives?
So I know the sampling rate, if I remember correctly, is 15 megahertz for this data and 10 megahertz for normal MFM. It ends up moving to a data transmission rate of 7.5 megabit per second for RLL and then 5 megabit per second for MFM. So.
Wait. 7.5 is wider than 5. So isn't RLL more compressed? Forgive me, I'm having trouble with the math in my head.
No worries. Yeah, 7.5 megabit would go faster than the 5 megabit,
Okay.
so that does account for the compression.
What I'm thinking about is the microseconds in between the pulses.
Right.
Sorry about that.
No worries. No worries. So you can see the peaks are well defined here. I don't actually have the log output for that first track that was corrupted, but what you see there is you'll have lower counts where these peaks are, and the number counts will be more spread out in between the two. So there'll be higher numbers here where there really shouldn't be many, if any at all. And so this, instead of being hills, you'll see kind of an averaged out line with higher values in between. And that's how Mr. Guestwine was able to interpret the head misalignment issue. Okay, so close that. And then go back over here. So, any other questions or comments, feedback? Cheers, jeers? No?
Well, we'll give you
Cool.
cheers.
Thank you, thank you.
Well, thank you.
Just thank you so much. In closing, I just want to give some shout outs to a few people. Dave Lovett, aka, again, Usagi Electric, for getting me down this rabbit hole. There you go. AJ, again, Forgotten Machines, for the help you have given and will give going forward. Mr. David Guestwine, for the original device and all the work he put into developing that. Mr. Paul Henningkamp, for his work in that Python script that got me going the right way and further down the chain on decoding. Tronics 286 from the Guestwine emulator Google group. He was the one, he or she, I'm not certain, was the one that developed the initial schematic for the original device that I built upon. Also, if y'all know June from Nibbles and Bites, she's also down on the exhibit floor. She helped transfer the hard drive down from Isagi's residence, about 6 hours away from me. So, again, want to thank her for her help in that. Not the least at all, and especially a huge shout out to my family for letting me go down this trail a lot longer than I should have on some days, but a huge thank you to them as well. So, and that's all I've got.
Thank you. Very nice.
Okay.